Hello everyone. So today's video, guys, is about explaining the theoretical aspect of buffer overflows. I will be explaining the basics of this attack in this video, and then we're going to move on fuzzing and how to identify buffer overflows during code reviews or exploiting buffer overflows in target systems. So guys, as you all know, guys, buffer overflows is basically when a memory area is given too much data for the allotted space or the specified space, and the memory area then naturally overflows. This overflow can then enable the attacker to execute their own specially crafted code or malicious code. I mean, normally it is like rootkit or Trojan horse. So to be able to understand buffer overflows, guys, I have put like simple slides where I will explain to you the basics before getting a handle on the buffer overflow or the practical side of buffer overflow. Let's take a look at this design over here, and you see the memory layout is like this. You have the stack, okay, and you have the heap, okay, and as you can see, guys, the stack grows downward while the heap grows upward. So the stack is an area of memory where you store temporary data. Okay, now it's like kind of fixed. It's kind of fixed memory. Okay, while the heap is dynamically allocated. It changes during the runtime or the execution of the program. The stack is fixed. You need to memorize these, guys. The stack grows downward. It's fixed in size, while the heap data or the heap area in memory is dynamically allocated. It changes during the program runtime. So here, the text segment contains the program code, okay? And you have the data segments contain the global information. Okay, guys? So let's move on over here. So as you can see, guys, the memory layout, you need to understand that. You have the heap, the stack, the global, and the program code, okay? Now, in this area, you got the temporary or the area of this, the memory area, heap area here is dynamically allocated as we said, and it changes, the size changes over the program runtime, while the stack is fixed, okay, and it stores, as you can see, the local variables and functions. And the program code, as you can see over here. So in general, guys, let's go back. When the program or application runs, it pushes data to the stack. And then as the program runs, the data is being pushed further and further into the stack. Thus, the stack moves every bit of data downward like this. Okay, every bit of data is moved downward. Okay, and every new bit of data is pushed to the stack at the top, and then it goes downwards, which is the opposite of the heap. You need to understand this mechanism, guys, because the ultimate goal of buffer overflow is to push data more and more to the stack to overfill the size of the stack. And once overfilling the size of the stack, the attacker will then push the, let's say, the malicious code to the area called return address or the instruction pointer. I'm going to explain that further. So let's go now to the Intel registers, guys. So Intel CPUs have general purpose registers that are used to store data. As you can see here, we have the EAX, which is the accumulator. We have the EBX, which is the base, the ECX, the counter, EDX, the data, and then we have the four most important registers, guys. For buffer overflows, all I need to understand is these four registers over here. Now, SI, the source index, DI, destination index, BP is the base pointer, SP is the stack pointer. And as I can see, there is a missing pointer over here, register, sorry, which is the instruction pointer. Okay. Now, the instruction pointer is very important and critical, which points to the address of the memory, points to the address of the memory area where the next instruction will be executed. Now, let's go to the anatomy of the buffer overflow. So here, guys, let me make this more big. So here we have the stack pointer, okay, and here we have the base pointer. Now, what does this mean, guys? So here it depicts the stack. This is how the stack looks like, okay. Now, at the top you have the stack pointer, and at the very bottom you have the base pointer. But as we said, the stack grows downward, which means that the stack pointer, okay, points to the top of the stack here. The top of the stack is pointed by the stack pointer, which is at the lowest memory address. Now, the highest memory address is, according to the sense of the stack, is at the very bottom, which is, what base pointer points to. The base pointer over here points to the highest memory address at the bottom of the stack. So that's how stack pointer and base pointer works. Okay, now the instruction pointer, as we said, contains the address of the next instruction the CPU is about to execute, which is here, the return address. Okay, now to be able to execute a buffer overflow, we need to manipulate the instruction pointer, okay, and get that instruction pointer to point to our malicious code, which means we need to overwrite the return address over here with our malicious code. How we can do that? We need instruction pointer to point to this area over here. All right, after we overwrite it with our malicious code. So let's go to the next slide over here. So now, as you can see, guys, data is put on reverse order onto buffer. Okay. Now, over here, guys, once the program runs, it's going to use the push instruction, okay, to push data to the stack. Now, the first bit of data goes here at the top of the stack. Now, whenever there is another bit of data, the stack will push the old one downward and puts the new one, okay, at the top of the stack. So to add any data to any stack, you need a push instruction in the assembler code. Push move the next increment of data into the stack like this. Okay. Now the stack stores data from top down. So new data is added to the top. Okay, and the existing data, like here, is all of these existing data move down. Okay. Now the stack pointer moves to a lower memory address. That's how it works. So when a program begins to run, a stack frame is created with local variables, functions. Everything is pushed onto the top of the stack. Okay. Now the key to the buffer overflow attack is to gain access to the instruction pointer, okay, which is here, or return address. If we can gain access to the instruction pointer and have that instruction pointer point to our malicious code, we will be successfully able to execute the attack. Now, as we said, when data is entered, it enters the stack in reverse order from here, okay? And then the stack grows downward toward the base pointer. If we can successfully, guys, push more and more data downward, okay, to the stack, so that we overfill the size of the stack, we can then possibly push past the base pointer. We're still continuously pushing data, pushing data to get past the base pointer, and then have the area or the stack overflown, and then we have the instruction pointer overwritten over here. The instruction pointer is in the return address. We have that overwritten with our malicious code. Okay, that's how it's going to work. The same principle applies over here. So, in a sense, the instruction pointer will point to our code and begin execution. That's how it's worked. So you're going to continuously push data more and more to the stack, memory here, till you get to the point where you overfilled the stack and you get to the return address. And then what you're going to do is to push your code to the return address and make the instruction pointer point to that address. Only and only then you have successfully pulled the buffer overflow. Look at this figure over here. So we pushed the memory area, the stack area, with hello strings. We were continuously pushing, make the stack goes downward, pushing data more and more until the stack reaches the return address. Now the stack here from this, the starting area from here till all the way downward here, the stack is overfilled with data. Now any extra data will go to the return address. The instruction pointer now points here to this hello, to the red hello. Now instead of the red hello, we're gonna push our malicious code and make the instruction pointer execute that or point to that area over here. So once you overfill the memory with, gibberish or, any data you want, once you overfill it, you now have the chance to push more data, the malicious data, okay, to return to the return address, and then have the instruction pointer points to your malicious code. That's in theory how it works. It's oversimplified, guys. I couldn't simplify it more than that. So in the next video, guys, we're gonna put that into practice. I hope you all understand that, and see you in the next video.